Just to confirm what we were just talking about the difference between post-tension and pre-tension when it comes to the anchorage zone. In pre-tension, the force transfer happened through the transfer length. So you have L sub D, if you like. While in this case, in post-tension, the point load is going to be just applied from outside on some bearing plate. And the performance of the concrete in post-tension is going to be the same as any other concrete block that you apply a point load to it. This stress distribution that you're looking at is a stress distribution in the y direction. If you like to consider this to be the y direction, up and down of the picture, and longitudinal direction is going to be called here x direction. So for the depth of nearly the size of the bearing plate, you're going to have some compression. After that, you're going to start to have here some tension stresses in the y direction. Look what happened here. When we start to move this point load, we start to have some eccentricity. What happened? If you consider here this to be like the bearing plate, and then you take a block which is going to be equal to, if I may take the block from here, and this block is going to be like a square block. So what I have done here, I have taken here the depth, right, total depth of the block for this square. You're going to be taking this y distance and just repeat it, just to draw this box, right, for this square, and then take the length of it to be the same as the height. So this is going to be the square I'm going to be working with. So here's the square, and this where you're going to have most of the stresses is going to be right here, and this is going to be almost nearly the end of this tension zone. So this actual depth, which is equal to 2 times y, is going to be nearly the end of the maximum tension. Maximum tension is going to be happening here within this box, and this where you're going to put the ties. So your ties is going to be like this. But excuse me for the color, because the color is not really showing what's happening. But if you like, I can just change this color here to, let's say, to green color, or to this cyan color.
Do you put any ties past where the tension ends?
Yeah, absolutely. You don't stop the ties. You're going to keep the ties for the total depth of the beam, for a distance equal to the total depth of the beam. But the actual ties and all the performance is going to be happening right here in this location. So in some designs, what they do, they put more ties in this location, right, around this area here, which means within a distance which is equal to the depth of this square, and then after that they start at some minimum ties. And once you come to the length, which is of this big square, which means the total depth of the beam is going to be the same as this length here, they can stop it after this. And some other design will just keep something minimum. They put, for example, number 3 at 14 inch. Just keep it as minimum. But the ties are really needed in this location. This is where you need them. So the good thing about this distribution here is it gives you an idea how would you put the ties. So when you have a case like this, you know, most of the ties are going to be right here, right at this circle location. If I may put it here, unfortunately, it's going to be also red. So I need to change also the color of this circle. So I'm going to be using same color as this cyan and make it a little bit bigger. So most of the ties going to be needed here. This is where you need to put the ties. It's going to be right in this location in a case like this. But you're not going to stop the ties. You're just going to keep it continuous. But you know that here, you just need the minimum. So again, some designs, which means it's going to be based on the designer. It's going to be up to you. You can just stop the ties right here, or you can just extend it beyond this limit. So in this case, as you see, most of the tension force and tensile stress is going to be within this location here. But if you start here to have this eccentric case, like when it comes to the stresses on the tendons, it's going to be eccentric. You need to know that most of the force and the tensile stress is going to be right here. If I may take this circle and repeat it right here, this is where you have most of the tensile forces and stresses. It's going to be right at this location. So now you have an idea where would you put most of these ties, where it is really needed, so you don't miss it. So the good thing about this finite element analysis, it gives you an idea about where the stresses is going to be, the tensile stress is going to be, and where you're supposed to put most of these ties. Any questions?
Do you usually use the same thickness of tie throughout the whole member?
Yes, you would. You don't want to change the tie size, but maybe you'd like to change the spacing. So in here, for example, if you like, you can put them at 3-inch or 4-inch spaces, right? And then after a certain distance, you're gonna start to lighten it up. So you're gonna put it, let's say, at 6 inches or 8 inches. And then after that, maybe at 4 inches, at 14 inches for the rest of the beam length. But for the tie size, you don't want to change the bar size. All right, any questions, other questions? Okay, we have 3 methods for the anchorage zone when it comes to post tension. This linear elastic stress analysis method, this is like more of analytical method that with this you can understand what's going on in terms of the stress distribution. For example, if I may take this method here and consider it to be like elastic analysis, right? Because this is going to be linear elastic analysis. When you do finite element analysis, this is going to be like linear elastic analysis. And if I'm able here to do to take strips, let's say I'm going to be taking segments here. Just consider that I'm going to be taking segments of this beam when it comes to my finite elements analysis. Going to be taking here a segment, and let's say this segment here for a strip is going to have a width of, let's say, 2-3 inches, right? I can control this size, whatever size that I'd like to go with. And then I can do here integration of the stresses. Any tension stresses here, I can just multiply the width of the beam, multiply by this length, multiply by the stress value, average stress value here, and keep on repeating this, right? I'm going to be taking another strip here, right? All the way to the end of this end block. So for each one of the strips, I can do integration of the tensile stresses, and then based on this, I can design a rebar and put right in the middle of it. You would call this elastic analysis. So it's going to be elastic analysis in this case, linear elastic analysis, because I'm not taking here any post, I'm going to say here, post yield or any plastic distribution of stresses. So this method, actually, if you like to consider it, and just, this finite element analysis is just used for research. It's not really used for an actual design, unless you have a supercritical beam and you'd like to have very detailed analysis for the elastic distribution, and this is going to be your design. But most likely, you're not going to be doing it this way. So now we have an idea about what does it mean by linear elastic analysis. Now, I'm sure if you guys heard about Strut time model. Anyone heard about Strut time model? Yes? No?
No.
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 All right, I can show you here. I'm gonna jump and show you maybe a couple of slides to explain it. And then lastly is gonna be this approximation, which means what's gonna happen if you'd like to have this in the code. Because don't forget, once you go to the code, everything needs to be simple. It needs to be straightforward design, analytical method, and sometimes they call prescribed, which means you have all the equations for it. People's just gonna be using it. They're not gonna be reinventing the wheel, if you like. So for this Strut time model, I'm going to jump here and show you, by the way, this is going to be like the bearing plate, and this is going to be this spiral. Usually they provide this at the end of the beam, right? This is going to be also to keep the concrete within this area here and prevent explosion of it. But let me show you the Strut time model, just to have an idea. So here's the distribution of the stresses. If you put here a point load for a post tension beam, right? And this is going to be the stresses. You're going to have here some tension. And you see here's going to be the depth edge. And within the depth edge, you're going to have some stresses going this way. Now, think about that in the edge distance away from the face of the loading, let's say at about edge distance, which means if I'm going to be taking here this square, if I put here a square, if I take this square here, and after this length, which is equal to the depth of the beam, the stresses would be uniform here at this point. It means I can take half of the stresses and put it as 1-point load, which is right here. And the other half of the stresses, I'm going to be taking it and put it as point load. So if I put here a point load, which is equal to P, after a distance of H, and here's H, is going to be having here 2 identical point loads. Each one's going to be coming from here. Now, if the force is coming like this, and at one point is going to split into 2-point loads like this, at certain point, you're going to have here, this is what we call here strut, and a strut, which means if you like to do this analysis, like the one that you do in truss solution or truss analysis, you're going to have here a point load. It's going to be coming like this as a compression. Another point like this is going to be coming as compression. And through this member, and this member is going to be just something that you consider to happen inside the concrete, you're going to have another compression force. It's going to be coming this way at this node. And if you have a situation like this, you have compression, you're going to end up with some tension force coming that way. Because in order for you to take the force, this inclined force, and transfer it into this force, you're going to have some tension force. And this is exactly where you'd like to put the ties, around this area here. Because the maximum tension force is going to be happening here. So we call this method here strut and tie method. So you're going to have a struts and ties. This is going to be like truss analogy, if you like. And this method is now currently in the ACI code. So you have a special chapter for strut and tie analysis, and you can figure out exactly after what distance this tension force is going to happen, and then you can complete your analysis and do it that way. So this strut and tie method is also now in the code, but it's not going to be that simplified. We have more simplified method when it comes to the design of this in the block, which is this approximation. With that, I'm going to stop for today. I'm going to be asking everybody to leave, and then please see me at the office hour to review your midterm.
Professor, I have a question.
Yes.
The quiz, should we expect it to be around the same length as the midterm or much shorter?
Not much shorter, but it's going to be shorter in time.
Okay. Should we expect conceptual questions?
Yes, you should.
Okay. Thank you.
No problem.
Professor,
Yes.
I had a question. So on the, are you going to be posting the PDFs or like the corrections that of the exam?
No.
No, you won't be? Okay.
No, because you have it in the slide sets. You have
Okay.
the exact analysis and you have the design in the slide sets.
Okay, sounds good. Thank you.
All right. Thank you.
Professor,
Yes.
do we need to use Proctorial for the quiz?
Yes.
Okay, thank you.
No problem.
Professor?
Yes.
So the quiz will be graded separate from the midterm, right?
It's going to be graded separate from it. And then at the end, it's going to be used to enhance your grade in the midterm.
Okay, so you will not choose like the higher grade. It will be just to...
Yes.
Okay, okay. Thank you.
All right.
Oh, one last question is:
Yes.
should we expect the entire class or just part of the class?
Everybody will take it. It's going to be useful for you. Even if you are happy with your grade, it's going to be important. Meaning,
No, I meant like is he gonna take the entire class period or should we just expect half the class?
oh, you mean for the time?
Yeah, time.
I'll give you enough time, but please study before this quiz.
Oh yeah, definitely.
I don't want to see like I don't know.
Get lower grades than what we got on the midterm.
Yeah. I don't want to come to a point that someone is failing because the performance was just bad, you know, in the midterm and the quiz. Otherwise, it's just, I mean, for certain people, unfortunately, they won't be able to pass this this class if they didn't do well in the quiz.
Okay, thank you.